Welcome to this new tutorial on mass balances, one of the most important tools in bioprocess engineering for the design and analysis of bioreactors. In the Bioprocess Engineering online tutorial series, I present the fundamental principles of bioprocess engineering and their industrial applications in microbial fermentation, enzymatic bioconversion, and animal cell culture processes. For more tutorials and updates, please subscribe to our YouTube channel or visit our website. This tutorial focuses on mass balance equations, which are among the most widely used relationships in bioprocess engineering. Mass balances are based on the principle of mass conservation. This principle states that during any process operation, mass may be transferred or transformed, but it can neither be created nor destroyed. As a result, the total mass remains constant throughout the process. For bioreactor design, two main types of mass balances are commonly used: initial final balances and instantaneous balances. Initial final mass balances describe the conservation of mass between an initial state and a final state during a process operation. These balances are expressed in units of mass, such as kilograms. They represent the simplest form of mass balance equations, although they are used less frequently than instantaneous balances. Their main applications are calculating the final mass of components at the end of a process and determining the amount of a component that must be added or removed to achieve a desired final condition. Instantaneous mass balances describe the conservation of mass at every moment during a process operation. They are expressed in terms of mass flow rates, typically in kilograms per second. These balances are by far the most widely used relationships in bioprocess engineering and are essential for many important applications, including kinetic analysis for evaluating reaction and mass transfer rates, kinetic modeling for predicting concentration changes over time, and bioreactor sizing for determining the required reactor volume. In this tutorial focused on instantaneous mass balances, we will explore how to formulate instantaneous mass balance equations and when and how to use them in bioreactor design and analysis applications. Let's begin with the first part: how to formulate instantaneous mass balance equations. The instantaneous mass balance is applied to a system defined by boundaries, such as a bioreactor. When applied to a mass component A, the balance involves four rate terms, commonly represented by four arrows: inlet rate, the rate at which component A enters the system through the boundary from the exterior to the interior; outlet rate, the rate at which component A leaves the system through the boundary from the interior to the exterior; reaction rate, in the presence of chemical or biochemical reactions. This term represents the rate of production or consumption of component A; variation rate, the rate of variation of the mass of component A inside the system with time. With its four rate terms, the instantaneous mass balance is written as inlet rate plus or minus production rate equals outlet rate plus variation rate. The production term is positive when the component is produced and negative when the component is consumed. Inlet and outlet rate terms represent the rates at which the mass of a component crosses the system boundaries. For bioreactors, these terms are most commonly associated with an inlet or outlet flow stream containing component A. For example, when a volumetric flow rate Q, liters per minute, enters or leaves a bioreactor containing component A at concentration Ca, the inlet or outlet mass rate is given by QCA. Inlet and outlet terms can also result from mass transfer across the system boundaries. For example, oxygen or carbon dioxide may cross the gas-liquid interface by diffusion. In this case, the inlet or outlet term corresponds to the rate of mass transfer of the component across the interface. The reaction rate term represents the rate at which component A is produced or consumed by a chemical, enzymatic, or cellular transformation. It is denoted by the overall reaction rate RA for the entire system, in kilograms per second or hour. This rate is often expressed as a function of the volumetric reaction rate, denoted by RA third, which corresponds to the rate per unit volume of medium. RA equals RA third V, where V is the medium volume. For cellular processes, the overall rate RA is also commonly expressed as a function of the specific rate QA, defined per unit biomass. RA equals QA x V, where X is the biomass concentration. The variation rate term represents the rate of variation of the internal mass of component A inside the system. Mathematically, it is expressed as the time derivative of the internal mass of A, dMA over dt. It can also be expressed as a function of the concentration of A, dVCA over dt, and when the volume V remains constant, this expression simplifies to VdCA over dt, the product of the volume by the time derivative of the concentration. In classical chemical engineering terminology, the fourth term of the balance equation is often referred to as the accumulation term, because it represents the accumulation or depletion of mass within the system. Personally, I prefer the term variation rate, because it more directly describes the change of mass or concentration with time inside the system, whether positive or negative, during the process operation. When applied to a bioreactor or fermenter, the four-term instantaneous mass balance can often be simplified, depending on the operating mode of the system. For example, in batch operation, there are no inlet or outlet flow terms. The balance therefore reduces to the two-term equation, plus or minus production rate equals variation rate. In continuous operation at steady state, the variation rate term becomes zero because the internal mass remains constant with time. The instantaneous balance relation then simplifies to inlet rate plus or minus production rate equals outlet rate. In the second part of this tutorial, we will explore how instantaneous mass balances are used in the analysis, modeling, and design of bioreactors. One major application of instantaneous mass balances is the kinetic analysis of enzymatic or cellular transformations in bioreactors. In this context, instantaneous mass balances are used to analyze experimentally measured concentration changes over time and to determine reaction rates or mass transfer rates. For the kinetic analysis of enzymatic or microbial transformations, the time variation of a component concentration is measured experimentally. As a result, the variation rate term of the mass balance, dMA over dt or VdCA over dt, is experimentally known. The instantaneous mass balance equation is then used to determine the reaction rate RA, while accounting for the possible contributions of inlet and outlet rates, depending on the operating mode of the bioreactor. From the overall reaction rate RA, the volumetric rate RA third, and the specific rate QA can then be calculated. Let us consider, as an example, the analysis of cellular growth in a batch fermentation. Experimentally, the biomass concentration X is measured as a function of time during the fermentation. For cellular biomass, the instantaneous mass balance is written as Rx equals dmx over dt, or using the volumetric growth rate Rx third V equals dVx over dt. Assuming that the reactor volume V remains constant, the equation simplifies to Rx third equals dx over dt. Thus, at any given fermentation time, the volumetric growth rate is obtained directly from the time derivative of the biomass concentration, represented by the slope of the tangent to the concentration versus time curve. The specific growth rate, denoted by mu, is then calculated by dividing the volumetric growth rate by the biomass concentration. At this stage, let me emphasize an important point. Reaction rates are often written as dC over dt, the time derivative of concentration. However, this is not the general definition of a reaction rate. From a conceptual point of view, a chemical or biochemical reaction rate is a physical quantity that characterizes the transformation rate of matter by reaction. It is not, by definition, a mathematical time derivative. Writing the reaction rate as dC over dt results from the instantaneous mass balance in the specific case of a constant volume batch reactor, when the reaction rate is expressed per unit volume. In all other situations, such as continuous reactors, fed batch operations, or variable volume systems, the reaction rate is not equal to dC over dt because inlet, outlet, and volume variation terms also contribute to the mass balance equation. Let's consider another example, the analysis of glucose consumption in a continuous fermentation. Experimentally, the glucose concentration GLU is measured over time as it decreases and eventually reaches a steady-state value. For glucose, the instantaneous mass balance on the continuous fermenter is written as Q GLU feed minus R GLU equals Q GLU plus dm GLU over dt, where GLU feed is the glucose concentration in the feed stream. GLU is the glucose concentration in the reactor and outlet stream. Q is the volumetric flow rate. Using the volumetric glucose consumption rate, AR GLU third, the balance becomes R GLU third equals Q over V, GLU feed minus GLU, minus D GLU over dt. Thus, for a continuous system, the volumetric glucose consumption rate is not simply equal to the time derivative of the glucose concentration. It also includes contributions from the glucose inlet and outlet flow rates. When steady state is reached, the time derivative d GLU over dt becomes 0, and the volumetric glucose consumption rate simplifies to R GLU third equals Q over V, GLU feed minus GLU. As a third example, let's consider the analysis of the oxygen transfer rate in an aerated stirred vessel containing water. The vessel initially contains deoxygenated water, and aeration is provided by continuously injecting air into the stirred vessel. The dissolved oxygen concentration is measured over time using an oxygen probe until the maximum oxygen solubility is reached. When applied to the liquid phase inside the vessel, the instantaneous oxygen balance simplifies to inlet rate equals variation rate. In this case, the inlet rate term corresponds to the rate of oxygen mass transfer from the gas phase to the liquid phase, denoted by JO2. The oxygen balance on the liquid phase is written as JO2 equals dMO2 over dt, or in volumetric form, JO2 third equals DO2L over dt, where O2L is the dissolved oxygen concentration in the liquid phase. Thus, at any instant, the volumetric oxygen transfer rate JO2 third is obtained directly from the time derivative of the dissolved oxygen concentration. A second major application of instantaneous mass balances is the kinetic modeling of bioprocesses in bioreactors. In this case, instantaneous mass balances are used to predict concentration changes over time from known reaction rate or mass transfer rate laws. Constructing a bioreactor simulation model involves deriving the mathematical relationships that describe the time-dependent variations in the concentrations of the different components in the medium. This modeling methodology follows the concept of the modeling triangle, which integrates instantaneous material balance equations, expressing the principle of mass conservation, with thermodynamic and kinetic laws describing the underlying physical and biochemical phenomena. For the kinetic modeling of enzymatic or microbial transformations, laws describing bioreaction kinetics, or mass transfer within the bioreactor, are first established. These laws allow the determination of the specific rates, volumetric rates, and overall reaction rates as functions of the component concentrations. The instantaneous mass balance equations are then used to calculate the variation rate term dMA over dt, or VdCA over dt, while accounting for the possible contributions of inlet and outlet rates, depending on the operating mode of the bioreactor. This leads to a set of algebraic or differential equations, describing the behavior of the medium components. The concentration profiles as functions of time are then obtained by solving or integrating these equations. Let us consider, as an example, the modeling of cellular growth in a batch bioreactor. Under non-limiting substrate conditions, cells grow at a constant maximal specific growth rate, denoted by mu max. For cellular biomass, the instantaneous mass balance is written as Rx equals dmx over dt, or in volumetric form, Rx third equals dx over dt. And by introducing the specific growth rate, mu x equals dx over dt. Since the specific growth rate is constant at mu max, the time variation of the biomass concentration is described by the differential equation dx over dt equals mu max x. By integration, starting from an initial biomass concentration x0, the biomass concentration as a function of time becomes x equals x0 exponential mu max t. This equation describes the exponential increase of biomass concentration during the growth phase. As a second example, let us consider the modeling of the dissolved oxygen concentration during the aeration of initially deoxygenated water in a stirred and aerated vessel. The volumetric rate of oxygen mass transfer from the gas phase to the liquid phase, denoted by JO2 third, is described by the mass transfer law at the gas-liquid interface. JO2 third equals KLA O2 star minus O2L, where KLA is the volumetric oxygen transfer coefficient. O2 star is the oxygen solubility concentration. O2L is the dissolved oxygen concentration in the liquid phase. When applied to the liquid phase inside the vessel, the instantaneous oxygen balance is written as JO2 equals dmO2 over dt, or per unit liquid volume, JO2 third equals dO2L over dt. Substituting the oxygen transfer rate law into the mass balance yields the differential equation, describing the time variation of the dissolved oxygen concentration, dO2L over dt equals KLA O2 star minus O2L. Integrating this equation from the zero initial dissolved oxygen concentration gives O2L equals O2 star 1 minus exponential minus KLAT. This equation describes the progressive increase of the dissolved oxygen concentration until it approaches the oxygen solubility concentration, O2 star. A third major application of instantaneous mass balances in bioprocess engineering is the sizing of process equipment, particularly bioreactors. In this case, instantaneous mass balances are used to determine bioreactor volumes from known reaction rate or mass transfer rate laws. As an example, consider a continuous enzymatic reactor used to convert a substrate A into a product B. A continuous stirred reactor is designed to process a volumetric flow rate Q, liters per minute, containing a feed substrate concentration Ca feed. The objective is to achieve a specified substrate conversion corresponding to a target outlet substrate concentration Ca. The purpose of reactor sizing is therefore to determine the reactor volume V required to reach the desired substrate outlet concentration. In a first step, the required consumption rate of substrate A, denoted by Ra, is determined from the instantaneous mass balance on component A. At steady state, the substrate balance is written as QCA feed minus Ra equals QCA. The reaction rate in the reactor is therefore equal to the difference between the inlet and outlet rates of A. Ra equals Q, Ca feed minus Ca. In a second step, the mass balance equation is combined with the bioconversion kinetic law. For the simple case of first-order kinetics, the volumetric reaction rate Ra third is expressed as Ra third equals Kca, where K is the kinetic constant. For a given kinetic constant K, the required reactor volume is then obtained by V equals RA over RA third equals RA divided by KCA. Thus, the reactor volume, necessary to achieve the desired substrate conversion, can be directly determined from the instantaneous mass balance and the bioconversion kinetic law. In summary, instantaneous mass balances, expressed as inlet rate plus or minus production rate equals outlet rate plus variation rate, are the most essential and widely used relationships in bioprocess engineering. Instantaneous mass balances are applied in all major tasks involved in the analysis and design of bioreactors, including kinetic analysis, evaluation of reaction rates and mass transfer rates, kinetic modeling, prediction of concentration changes over time, bioreactor design, sizing of reactor volumes. Instantaneous mass balances provide the fundamental framework for understanding, modeling, and optimizing bioprocess operations. If interested, you can gain a deeper insight in mass balances by enrolling to the online course, Bioprocess Engineering Basic Principles. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.